Okay, so let me ask you kind of a different question. I mean, there's lots of physics problems we can solve, but it's good to kind of turn the page here and ask a slightly different question. Suppose you wanted to find a differential equation which had a certain geometric property, right? Let's see here. Like suppose you wanted to find a family of curves, right, where the slope of the curve was always twice the what's the word? The y value of the curve at each point. How would you find such a curve? So here's a question. Suppose you want curves whose slope is the square of their y value. I mean, this one's kind of stupid, right? I mean, what differential equation would you solve? What if instead of saying square, I just said was proportional to their y value? What does proportional mean? Yeah, that would be directly, that would just be, see, proportional implies a proportionality constant. So like this would be dy dx equals to like say k times y, right? There we'd have the slope is proportional to y. You can separate and integrate. This is a very famous problem, right? This is exponential growth. Oops, I spilled the beans. So we get natural log f value of y equals to kx plus a constant. Do algebra, you get y is equal to, you know, e to the c plus or minus e to the c times e to the kx, or just y equals to, let's say, well, how about why not? I mean, why not? Why not e to the, sorry, that's awful. I stand by it though. All right. So exponential growth. Well, you can understand this geometrically. You're looking for a family of curves whose slope is proportional to their value, right? So what about the black, what I wrote in black? What differential equation would we want to solve if we were looking for curves whose slope was proportional to the square, or let's just say equal to the square of their y value to get rid of the k? We solve what? Slope is dy dx, right? And y squared, right? I mean, just solve that, and that should tell you what that family of curves is, right? So we get dy over y squared equals to dx minus 1 over y equal to x plus a constant, right? So what's this give us? This gives us y is minus 1 over x plus a constant. Yeah. Interesting. There's a really big difference between the purple one and the black one, right? Like, what's the domain for the purple one? I mean, they're exponentials, right? X goes to plus or minus infinity. No harm, no foul. I mean, it gets really big or really small. It goes to 0 in one direction or the other, depending whether k is positive or negative, but this has got a domain of the reals. This, on the other hand, something funny goes on when x is equal to minus c, right? So there's some kind of, like, you can't keep up, you can't satisfy this equation for too long. I mean, you run into trouble trying to maintain this over a domain. You can't do this for the whole reals, right? There's going to be some asymptote somewhere. It's like it grows too fast, right? Now, you can do other things. Like, suppose you want, I mean, you guys can tell me things like this. What if I had dy dx equal to y squared? Like, oh, I just did that. I'm an idiot. What could you say about this, by the way? I mean, there's this or, I almost forgot, y identically 0, right? Ignoring the y identically 0 solution, what can you say about the solutions? Are they increasing or decreasing? The idea I'm trying to get you guys to think about is if you're given solutions to a differential equation, right? You're given a statement about the derivative. So everything you learn in Calculus 1 is still fair game, right? You just got to think a little bit. This is greater than or equal to 0, right? Because it's the square of a real value. But that's also the derivative, right? Which describes the change in y with respect to x. So I can see that the solutions to this are increasing from direct analysis of the differential equation itself we're solving. In fact, this one's constant, and these ones are strictly increasing. They're always increasing everywhere, except where they're not defined, right? X equal minus c. Yeah. But you can play these sorts of games. Like I have an example here where I create a differential equation where I say find a family of curves which is increasing for y less than minus 2 and y greater than 2, but it's decreasing between minus 2 and 2. So if you play with expressions a little bit, it's pretty easy to see that y plus 2 times y minus 2 does the trick, because if you just think about graphing y with 2 and minus 2, right? And you look at y plus 2 times, well, that's fun, y minus 2. It's fairly obvious that you're going to get like, you know, plus plus over here and minus minus over here, and between here you get a plus minus, I think. Yeah. So it's going to be negative, positive, and positive, which means the solutions to this differential equation are going to be increasing and on the ends and decreasing in the middle. So all the solutions to this differential equation will have that geometric feature. Right? Every last one is going to behave like that geometrically, and the details of the solution here involve partial fractions, and it's kind of a pain, but there it is. And I even have a plot. You know, you could use p-plane to do this, sorting through the things I talked about, or you could look up this thing. There's a way to plot. You can find other tools which just plot dy dx. It's isocline field, or it's slope field if you like, and solutions directly. These circles are just where I've clicked, said, hey, I want to see the solution, solution, solution. But if you look at it, you can see they're increasing above and below the y equals minus 2 and y equals 2 line, right? And they're decreasing in between. This is very similar to the population growth. So population growth, what's exponential population growth? Like dp dt equals to what? Kp. This is exponential population growth, right? Biologists like this. Exponential growth. So this is good for, like, you know, bacteria in a petri dish or something, right? But there's a modification to this that looks like the following: dp dt equals to k p, and then you do 1 minus p over c, something like that. So what we've done is we've taken the exponential growth and we've multiplied by this factor. What happens with this factor? Well, if p is close to 0, right? Think about limiting cases here. If p is close to 0, well, this is just basically exponential growth, right? But if p is what? If p is equal to c, what happens? This is 0, right? So we get constant population when the population is equal to c. And then you can draw a sign chart, right? Here's population. Well, here's I'm going to plot dp dt on this chart here. I don't know about you, but negative population doesn't make much sense. I'll put population 0 here. All right. Not infinity. No. I mean, you could talk about infinite population, I suppose. Population 0, population c, and what's the story? If p is less than c, this is positive. That's positive. We're assuming k is positive here, okay? So we'd have positive population growth. If p is above c, what happens? this becomes something less than 0, right? If p is, how to say this? P is greater than c, rather, I should say. If p is greater than c, then this is a negative number, so it's negative, right? How about, so what does this say? The population increases if it's below c, it decreases if it's above c. You can solve this, and its solutions look very much the same as that. This is the so-called logistic growth model. Now, I'm not going to go through that, but you can solve this. Use separation of variables. It's just a pain, right? You see you got dp over kp times 1 minus p over c equals dt. You separate, integrate. It's a rational function in p, so you can do the integral. And when you do that, and you plot solutions, what you find out is that it looks much the same as what I'm looking at. We have the population equals to the so-called carrying capacity, and the solutions look something like this. So, oops, I can't do it right. There's an inflection point at c over 2 for all the curves. So if I did it right, it's concave up here and it's concave down. There's a point of inflection for every solution curve when you hit half the carrying capacity, if I recall correctly. How would you prove that the inflection point was at half the carrying capacity? How would you figure out such a thing? Yes, you could say solve it and then take the second derivative, right? Or, I mean, nothing wrong with that, but here's a much lazier way to do it. Differentiate this. See, this says that p prime prime is equal to kp prime times 1 minus p over c, right? Plus kp times minus p prime over c, right? There's a p prime common here. There's a k common, so I can factor out kp prime times what? Times 1 minus p over c, right? Minus p over c, which is also known as kp prime times 1 minus 2p over c. So if we set this equal to 0, that is going to happen when p is equal to c over 2. When the second derivative is 0 at half the carrying capacity. So I'm trying to encourage you is you can think about solutions to differential equations. Yeah, you can solve it and then do things to the solutions like you already know how from calculus, or you can look at the differential equation directly and do analysis from that perspective. This is, I think, a new idea. All right, so show you some other examples here. I've got some more orthogonal trajectories examples in here. Here's the, this one's the minus bv squared example. So I did minus bv for you guys in class. Here's how it works out for v squared. I think I've put both of those on tests before. I usually ask about that on a test. Sometimes I'll ask about Newton's law of cooling. I cover this in calculus 2 as well. So Newton's law of cooling, it says that the rate of change of temperature is proportional to the difference of the temperature and room temperature. And it's kind of interesting in the sense that there are two parameters here, room temperature and the coupling coefficient. So it's not really a single differential equation, it's really a family of them. So you need two pieces of data to find a solution in this case. But anyway, here's a nice example of Newton's law of cooling. You can look at in a problem, if you look at a circuit, right? How many of you are electrical engineers? 1, 2, 3. How many are not electrical engineers? So you, what kind? Mechanical, 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 mechanical. Your responses are very mechanical. Let's see here. So, sorry, that was really pretty awful, but I stand by it. Let's see here. So this is the circuit we're talking about. Resistor, inductor, right? So inductors do what? They resist a change in current, right? And so like Ohm's law says we get I times R voltage here. This gives us L di dt. That's basically the definition of self-inductance, the inductor generates that voltage as a response to the change. No change in current, no voltage across the inductor, right? The current's steady, and there's no voltage there. But anyway, if you look at Kirchhoff's voltage law, there it is. But what is that? That's a first-order differential equation. In fact, it's a linear differential equation. You can solve it with the integrating factor method, and you'll find the current as a function of time for an RL circuit. There it is. You can also solve mixing tank problems if you have you can talk about salt into and out of a tank, and basically you set these things up as like dy dt equal to the rate in minus the rate out. And so for this one, I think I'm putting pure water into the tank. So the rate in is 0. The rate out is minus y over 100, because basically y is it's the kilograms of salt in the tank at time t. 100 is the amount of liters in the tank. So this gives us, anyway, once you sort through the units, this is the rate at which salt is leaving the tank in kilograms or something like that. And then you integrate and separate. I mean, the math here is not new. The setup, probably new. Let's see here. I'll show you a more exciting one here. We're almost out of time. This actually is the logistic growth math right here. This is how to solve this one. The notation's a little bit different, but that is the logistic growth problem up to a choice of notation. Fun fact, if you look at old differential equations books, there's a paper from about 1920 by two guys. They found that according to the logistic growth model, the population of the US is 210 over 1 plus 51.5 e to the minus 0.03 t, where t is the number of years past 1790, and it's in millions. So this says that 210 is basically the carrying capacity of the US in terms of population. So just, cautionary tale, don't believe population growth models. They're wrong. You just can't anticipate the future. You don't know what's going to happen. You don't know what technology we're going to find that allows us to support more biological life on the basis of less resources and so forth. It's unknown. We just don't know. And so here's a more complicated problem. At the end here, I have a rocket flight. I've got the hardest problem I have in this whole section is this one. Of a flexible rope of length 4 has 3 feet coiled on the edge of a balcony, and 1 foot hangs over the edge. At t equals 0, the rope begins to fall. All right? So how long does it take for the rope to fall completely off the balcony? So the thing that makes this really different from anything we've looked at so far today is that it's the mass which is falling is variable. Depending, more rope, more falling, right? So the normal force opposes gravity on the table, but the part which is hanging off doesn't have a normal force to oppose it, right? So anyway, so you actually have to do ddt of mv, but m has a time dependence. So you end up needing to solve lambda is the mass per unit length, lambda dx dt v plus this. It gives you this lovely differential equation. And this actually requires the special integrating factors, which I never really cover in their entirety in here. That's the section 2.5 stuff, but you actually need to use that to solve this problem. This is an example of where special integrating factors actually come up in a real physical problem. On occasion, I'll assign this as homework. But anyway, that's, I think, a fun problem. I usually regret assigning it, though. So we're just about done then, guys, with chapter 2 of my notes. Tomorrow we start in chapter 3. I think I promised I would show you one example today, so I still owe you it. This will take us all of 30 seconds. Here's your preview. Y prime prime plus 3y prime plus 2y equals to 0. The way we'll ultimately learn to solve this is the following. We write down the characteristic equation. We factor it. we read solutions, and we write down the solution. I don't know about you, but I think that beats the pants off reduction of order and the v/dv/dx trick. Yeah. It's not special to that one either. But this is a machine that it takes me about an hour and a half to build properly. So we'll spend considerable time tomorrow working our way to this understanding. Thanks, guys. You can't